In this video, I'm going to demonstrate how to conduct multiple discriminant analysis in JMP. So MDA is a statistical technique when your dependent variable is a categorical and your independent variables are metric variable and which are the continuous variables. So using multiple discriminant analysis, we can divide the objects into multiple groups, and it is like logistic regression, but one advantage with multiple discriminant analysis is that we can have multiple categories of the dependent variable. In binary logistic regression, we have only two categories of the dependent variable, which may be, for example, male, female, yes, no, and similarly 0 and 1. But in multiple discriminant analysis, we can have multiple categories of the dependent variables. So here the idea is that we create a function something like this, and I just supply the data point to that function, and that function is going to tell me to which category the data points belongs to. So how to conduct this multiple discriminant analysis? To demonstrate this, I have taken a dataset HB80 which is shared with you in the class. Now in this dataset, from x6 to x18, these are the independent variables. These are the characteristics which can be used to identify where the person, from which location the person has done business, and that information is contained in x4 variable. X1, if x4 equal to 1, that means the person is based out of US, and if x4 is 0, that means the person is not based out of US. They may be from some other region. Now, as I mentioned earlier, that the dependent variable has to be categorical. So therefore, the first change I need to do here is to make this x4 as a nominal variable, okay, because it can take only two values, 0 and 1, and apply, and you see that x4 has become a nominal variable. Now we know from the guidelines that for discriminant analysis, all the independent variables, they should be continuous, and they are continuous. We can see from this symbol. Now how to conduct discriminant analysis? Go to analyze. First of all, we need to make a validation column. So what I want to do here is I want to create a validation column. That means I will divide my data into training and validation. The model will be fitted on the training data, and it will be validated using the validation data. To create a validation column, go to predictive modeling and make validation column. No need to provide any input here, just click on OK and specify the rates or relative rates, whatever you want to specify. I'm going to keep it like 75% training set and 25% validation set, and click on go. So column has been added at the end. Now we can do the discriminant analysis. For that, click on analyze, go to multivariate methods and choose discriminant. Now here x4 is the category, and from x6 to x18 we will supply to the covariates. Now click on OK, and before clicking on OK, we have to also tell that I'm going to use the validation column which I created, so that it recognizes that which data points belong to training, which data points belong to validation, and click OK. So you will get this output. Now let's focus on this output, that what information do we get. First of all, it will give you the confusion matrix. Since it's a classification technique, therefore how the accuracy will be determined, it will be determined based on the classification matrix. So you can easily identify what are the true positive, true negative, something like that. For example, here this particular cell represents a true negative, this cell represents a true positive. So this is on the training, this is on the validation. The same thing which is given here in the numbers is translated into the percentage. Here also it gives some more information, that how many data points were in the training, how many were in the validation, what was the number of classified, misclassified, all that kind of things you can get from here. Now this is known as the canonical plot. We know that when the number of discriminant functions, they will be always 1 minus total number of categories minus 1. So here we had two categories, to which to classify, and that we can, and by using only one discriminant function we can classify it. Now if you look closely here, the canonical one is the function which is going to classify our data into 0 or 1. Towards the right we see 1, towards the left we see 0. So that means if this discriminant function on canonical function score increases, the data point belongs to 1 category, okay, which means inside US. If canonical function decreases, that means the data point belongs to 0, that means outside US region. So how discriminant function will work is that we are going to provide it the data point. That data point will be entered into the will get entered into the discriminant function. It will calculate the score. Now if that score is on this side, that means the data point belongs to 1. If that score is towards this side, then the data point belongs to 0. From discriminant score we can see that what is the actual and predicted value for each data point that we considered. Here it gives you the probability of the predicted value. Okay, for example, here the actual value was 1, that means it belongs to first category, first data point, and our model also predicted 1. Here it belongs to 1 actually, but our model predicted it to be 0. So this kind of misclassification and right classification will be listed here. If you see others here, so basically what it is saying that there is 77% probability that it is going to belong to 0, but 23% probability that it is going to belong to 1. So it is not going to give the misclassification probability to every data point, only where it finds it is less than 0.9 confidence, something like that, or 0.9 probability, it will give you these others option also. For example, here the data point belongs to 1, it said yes it belongs to 1, but the probability is 0.8675, and that's why it is saying that 13% probability that it may belong to 0 class. But you won't find these things everywhere, only where there is a less in which the model is less confident to which class it belongs to, only there it will provide. And from here you can generate other outputs also under this red triangle. For example, you can go for the stepwise variable selection. So right now the model that I built was based on all the variables. Now since it's a statistical method, we can have testing for significance also using p-value, so that we need not all the variables. For example, if we just want to retain only significant variables, that also we can do. Now you can do the stepwise variable selection in the discriminant analysis also. Sometimes if you click go, it will give you the answer in one click only, for example something like this. But the best way is that we do it manually. So by by variable selection, what we can do is we can systematically add the variables into the model. Now what variable we should add? Obviously for which the p-value is less than 0.05. So click on step forward, and the first variable will be included in the model, which is x17, and the p-value is less than 0. Then again click on step forward. The second variable that was included is x11 and it is significant. Then again click on step forward. Then third variable that was included is x6, p-value is less than 0.05, which is fine. So we have to keep on doing this until or unless we reach a stage where we don't have any other variable whose p-value is less than 0.05. Now in this process also remember that as you add the variables, the already added variables may also become insignificant. So we look how to remove them, but the first step is that we add the variables stepwise. So what variables we are going to add? Only the variables whose p-value is less than 0.05. Now again click on step forward. x12 variable was added, which means, and the p-value is less than 0.05, which is fine. Again click. Now x7 variable was added, and the p-value is less than 0.05, fine. Again click step forward, and now the new variable was added, x13, but the p-value was not less than 0.05. So at this particular point we should stop. because adding this x13 variable actually is not doing any benefit to us. Now what we are seeing here is that already added variables like x6, okay, the p-value is greater than 0.05 only by some small amount. We can now do this backwards selection, okay. Now what it will do, it will systematically remove all the p-value variables who had p-values greater than, or sorry, yeah, greater than 0.05. So this is known as the stepwise variable selection. Again, I'm going to repeat how to do it. First of all, we are going to add the variables, or the software will do it for you automatically. We are going to add those variables whose p-value is less than 0.05. So first variable that is added is x17, the p-value is less than 0.05, fine. Now click again here. Next variable that is added is x11, p-value is less than 0.05. Click again. Next variable that is added is x6, p-value is less than 0.05. Next variable that is added is x12, p-value is less than 0.05. And the next variable that is added is x7, again the p-value is less than 0.05. But as soon as we add x13, the p-value is greater than 0.05 and we should stop. So I can uncheck, and that means only the variables at most that should be in my model should be x6, x7, x11, 12 and 17. Now in this process what happened, due to something known as the partial correlation coefficient and all, the x6 variable became insignificant. That means the other variables that we added actually are doing almost kind of a similar work that x6 is doing, so we need not these variables. So what you can do is you can click on step backward. It removed x6 automatically, and just see that if all the variables that are contained here, they are significant or not. So all the variables are significant, that means apply this model and a new variable, new plot will be, function will be calculated here, which gives you the new results. So only x7, x11, x12 and x17 are the required variables in the discriminant analysis. And we can do other things also. For example, we can click on ROC curve option here, and it will give you the ROC curve. So it's surprisingly good. Doesn't matter which class is of our interest, maybe 1 or 0, the area under the curve is 0.9632, which is quite okay, very good score. You can click on this red triangle. You can also click on show canonical details. Okay, now canonical details is going to tell you, it will conduct different tests. It will tell whether overall discriminant function is statistically significant or not. We usually look at the Wilks lambda or Pillai's trace. Usually Pillai's trace is considered to be more robust. Therefore, as per Pillai's trace, the p-value is less than 0.05. That means the overall discriminant analysis or discriminant function that we have generated is significant. Remember, if there are multiple discriminant functions, it will give the p-value for those multiple discriminant functions. But here, since we had only 2 classes, for 2 classes there will be 1 discriminant function. For 3 classes there will be two discriminant functions. So Pillai's trace is significant. So that is one of the things that we have to consider here. Then also we can look at canonical option and show canonical structure. Now in the canonical structure, it tells you that what is the correlation between kind of a thing between the canonical score and the your variables. So x7 is positively correlated. That means if we increase x7, canonical score will increase. That means it will go towards this particular side, right hand side. That means the data point is more likely to belong to class 1. Similarly, if it is x12, the correlation is around 0.50, and that means that if we increase x12, it's going to increase the canonical function value towards right, it will go. That means it will belong to class 1. And similarly, we can look at other things like between canonical structure. Okay, it's like how canonical, so whatever is given here, it is just given in this form, that positively correlated or negatively correlated. Class means also you can generate what is the average value here of the canonical score. It belongs, if it belongs to 0, data point belongs to 0, and for the data point belongs to 1, what is the canonical class mean, basically what is the mean value of the discriminant function. So using these things, and similarly you can look at the discriminant score. So this is how you conduct the discriminant analysis in JMP.